Okay, I think we'll get started. So good afternoon and welcome to this session. This is the session Using EMET to Disable EMET. And our speakers today are Abdulellah, Alsaheel and Raghav Pande. We are in room South Seas ABE, so if this isn't the session you're expecting to hear, you're in the wrong room. I have a few notes before we get going. The first is to get you to stop by the business hall located at Bayside AB during the day. And for the welcome reception, the most important piece tonight is 5:30 to 7 in the same room. The Black Hat Arsenal is on the Palm Foyer on level 3, and you can join us for the Pony Awards in the Mandalay Bay BCD at 6:30 this evening. So just as a quick reminder, if I can get you to put your phones on vibrate, I know that's a lot more fun, but if we can just avoid interrupting the session. And without further ado, take it away.
Thank you. Hello everyone, my name is Alsaheel, as he said, and my colleague here is Raghav Pande. We are from FireEye company. We will be introducing a new technique to disable EMET using EMET. So you cannot see from here. Can you handle the slides?
Yeah, sure. Go ahead.
So I'm a consultant at Mandiant, Saudi Arabia Riyadh office. I used to work as an embedded software developer for some local company in Saudi Arabia. My current research focus is endpoint security systems, things like EMET. Second slide.
Done.
My friend here is Raghav Pande. He's a researcher at FireEye Bangalore office. He is working on the embedded doing the endpoint systems, like mostly things like EMET for the company. And also, I'm not finished yet.
There you are.
It's fine.
It's we'll go that way.
Okay.
Sorry.
No, we have lost the battery for the slide, so it's yeah. So there is a funny story about behind this meme. So I remember I have came across a post for some forum over the internet, and there was a guy who claimed that he found a new technique to disable EMET, and without back that up with any without any proof concept. So people starting to make fun of him, and for that, some of the comments actually were mean a bit, and some of the guys suggested that yes, you can disable EMET using add remove programs, and this was a bit funny, and not only this but also aspirational to me at least. I found that, let's say, we all know that add remove programs also can wipe the program off the disk, but also one can think of a similar thing, let's say a portion of code that wipe out the application from the memory itself. And this is what leads to our technique here. There is something that is equivalent to the add remove programs that wipe out EMET from the memory rather than the disk. So we'll be focusing on introducing the new technique to disable EMET using EMET, and we will demonstrate that at the end of the session. But before that, we will introduce EMET. We will talk briefly about its protections, and also we will go quickly through the previous techniques to disable EMET and previous evasion mechanisms. And we will end with summarizing a bit about having a custom anti-exploit solution, and we'll have some time for the questions. So EMET is a security detection tool from Microsoft that adds security mitigations to the user land protected programs. Beyond these protections built in the operating system, one could really think of EMET as an anti-exploit system, simply like this. The main reason for EMET, the main purpose, is to raise the cost of exploitation rather than prevent the exploitation. It works mainly by injecting its DLL to the protected programs. And mainly it works and depends on the inline hooking. And we will discuss what the inline hooking in the next slide. And it does various changes to the protected process, like adding new exception handlers to the process and manipulating the debugging registers. So we can see the load library. We can see the load library function, which is a Windows API. And we see that it has been how the inline hooking working. We can see that there is a detour at the top of this function. This detour is merely a jump to the detouring functions. So we see the detouring function in here on the right side. This is where Emmet implements its protection. So Emmet, basically, any code will call load library will take this jump first to the Emmet detouring function, which will Emmet analyzes this caller code to see if it's a safe code or not. And then if it's a safe code, Emmet will end up in jumping into the function prologue. So this function at the right bottom corner, it's the original prologue for the load library. At the end of this, there is the jump which gets back to execute the rest of the load library function. And this is how the inline hooking is working for Emmet. So we'll talk a bit about Emmet protections briefly, because some of the audience may not be familiar with Emmet. So Emmet comes to enforce some of the protections, like the SEH OP, which is the structured exception handling override protection, and the DIP, the famous DIP, data execution prevention, and we have the ASLR also. So all of these, Emmet can enforce them, no matter the underlying system, and no matter whether if the protected application has the module have been compiled with these options or not. It doesn't really matter, because Emmet will enforce these protections. Also, Emmet prevent the famous allocations, type of allocations in exploits, like null page allocation and the heap spraying. Also, Emmet gives an important feature, which is the EAF. This feature meant to detect the shellcodes, typical shellcodes, like Metasploit shellcode, which iterates over in the exported address table of modules like kernel 32 and kernel base and NTDLL. So Emmet implements the debugging register, and it uses them to place a hardware breakpoint on the exported table on these modules to see if there is any thread tries to access this exported table. And when this happens, it stops this thread and it will analyze whether if it's a safe code or not. Also, Emmet imported an important protections against the ROB attacks, the return-oriented programming attacks, from ROBGuard project. So some of these protections, like memory protection checks, which gives additional monitoring to the critical Windows APIs, like virtual protect, which could be used to mark the stack as executable and to bypass DIB. Caller check, which can be used to detect any Windows API gets called with call instruction rather than in jump instruction or return instruction rather than call instruction. Also, it detects the stack pivoting, and it has another feature, which is the simulate execution flow. And this feature emits when it returns from a critical Windows API, it manipulates the ESP, the stack register, and it will see if it's it will simulate, and it will see if this is a context of ROB gadgets to detect if it's a ROB attack. Also, it adds more randomization for the bottom-up allocations through bottom-up ASLR. Bottom-up allocations like heap and stack. Also, it adds additional checks on the load library API, so it prevents loading libraries through the network through universal naming convention paths. So Emmet also hooks even the lowest level of API things in the NTDLL, and also it tries to stop the attacks or the attackers who are trying to bypass Emmet by jumping over the installed detours. This is the anti-detour protection. It also gives the user the ability to configure a list of banned functions, so these functions cannot be used within the protected program. It also adds more verification and checking to the certificate chain trust. And also it gives the user the ability to configure a list of modules that not to be loaded for a certain program. This is the ASR. And we have the EAF extension plus. This is an extension to the EAF protection to detect the stack pivoting and PE header reads. So here we will discuss some of the previous technique to disable EMET. Mostly things published by Offensive Security. So in EMET 4.1, there was a global variable exported in writable data section. EMET actually was using this global variable at this offset of EMET DLL. It was every protection in EMET was checking for this variable. If it's 0, then it will not be activated. So simply anyone can just zero out this variable and the EMET protections will go unactivated. We have carried the same kind of analysis on old version of EMET 2.1. We have found it has the same weakness. So basically we think, or we suspect at least, that this protection is found like in early versions of EMET. It has been there, but nobody noticed maybe except in EMET version 4.1. To disable the EAF protections, it requires a special treatment. So this is the EAF, which is capable of detecting shellcodes. So basically, this is, since EMET uses the debugging register, anyone should have to clear out the hardware breakpoints, which are implemented by the debugging register, can disable this protection. To do this, one way is to use the context structure to get an access to the debugging register. We can see the DR0, DR1, DR2, DR3. These debugging registers are being used with EMET to detect the shellcodes. So zero out these registers to disable the EAF protection. And then one should need to use the NT-set context thread to set this zero out context structure to the current thread and then disable the EAF protection. For EMET 5.0, Offensive Security have found the same issue, but this time the global variable is placed on the heap rather than on the data section within a large structure. Offensive Security named that config struct. So at a certain offset in the EMET DLL, there is a pointer to this large structure. And then within a certain offset, there is this global variable. Zero out this variable and EMET protections will go unactivated. To disable the EAF, they have found there is an unhooked pointer, undetoured, let's say, to the NT-set context thread, which should be used to assign the zero out context structure to the current thread and then disabling the EAF. For EMET 5.1, it's the same thing happened again, but this time the large global variable have been set on read-only memory instead of writable memory. But they have found there is unhooked pointer to NT-protect virtual memory, and they have used this unhooked pointer to that API to mark this page as writable, and then they carried the same attack the same way. Raghav?
Yeah.
Thanks.
Right. So, so the techniques for EMET evasion. Now, what Abdulellah mentioned in the previous slides were they were like disabled. So you go ahead, you chase one offset, and then EMET goes away. So it's like that. But essentially, what we can do is we can boil down to each and every protection that comes in and individually try to break them apart. Now, this slide will be about that only. So the most used protections, statistically speaking, which usually thwart the exploit kits or the public exploits that come in through, are stack pivot, collar check, sim exit flow, and EAF. The first three use inline hooking to calculate whether the return address belongs to any return-oriented programming gadget or not. And the last one uses hardware breakpoint along with exception handling to check whether they are validated or not. So amongst the most used protection, as in case of stack pivot, we have 2 bypasses as of now. The first, both are not new. The first one was, I think, shown by Mr. Jared DeMott in his paper on defeating EMET 4.1 in Chromium. And the second one was, which we found in the wild in Operation Clandestine Wolf, which FireEye discovered, the usage of custom class to eventually make sure that stack pivot check fails out. So the way the stack pivot check works is when you pivot from a normal exploit, so you have to convert the stack pointer to make sure that it points towards a controlled region in heap. So the stack pointer will be differentiated and it won't be lying in the region that stays in thread environmental block, which is the stack's upper limit and lower limit upon the initial thread creation. So EMET basically checks upon any API hook, whether any critical API when it's being called, that the stack pointer is within that region or not. In case of most exploits, in fact, every one of them singly, what happens is the pointer is not within that region, so EMET blocks that. So in order to avoid that, what we do is the first is stack switching. So basically this is a rough layout. I hope you guys can see that. So what you do is instead of executing the gadgets on heap exactly, you make sure that all the gadgets are pushed to stack one by one. Stack is negated, and after that stack is again reversed back. So in this case, the first instruction is you exchange a register with stack pointer, and then you prepend and append a specific set of instructions to all the gadgets again and again in a repetitive manner. After that, everything goes on to stack, and you can execute the same thing. And when you call an API from that, the stack pointer will be in the original stack location, so the lower region and the upper region, as in the lower limit and the upper limit of the stack regions, will be validated. The second one is a custom class. So this was found in the wild in Operation Clandestine Wolf. Now, what the attackers did was basically they created a custom class and they created a virtual function inside that. Now, the technique of universally reading and writing any region of memory it's quite known since a long time using flash vector objects. So what they did was they called the custom class in such a manner that it required a lot of arguments, and they put up all the arguments as the rob gadgets that they wanted to execute. Now, when the code got converted to just-in-time compilation, basically all the gadgets were supposed to be on the stack when the function got called, and because we can override the function pointer, we can point it to anywhere else. But the thing was, the parameters are in the stack somewhere downward, so it's not directly aligned, so you cannot just do a ROP sled or stuff like that and just return again and again into the same thing. So we had to find a gadget in which it was like add ESP, 0x58 or something like that, and that would slide the stack pointer exactly into the parameters that were previously crafted into the stack. And eventually the attackers found out that this is the best mechanism to avoid stack pivot, because there will be no detection when we call an API. Amongst the next check, the caller check is the one which is the most prominent one. It basically checks whether, so let's say that there's an API that is getting hooked. When EMET gets the callback for that, it will check whether the return address for that API is preceded by a call instruction or not. And then it checks whether that call instruction will point to the API that was hooked or not. So in case of, even if you try to forge that, it will basically validate whether the destination is proper as well as the source is proper. And after that, it will simply either terminate or give it a green flag. And for that, either we use a call gadget, as in we find a gadget which basically calls an API and then returns, or we can use return into shellcode. So I think this is very obvious. So what you do is you find out a call register return gadget, and you populate the register with the value of virtual protect or any single API that can be called to mark a shellcode as RWX, and then you can point to that. So because all this we are doing just to mark our memory as RWX, so we have to make sure that we just follow one API and it works out. So in this case, it's called pointer dereference by ECX and return. So ECX points to the virtual protect's IAT inside MS-HTML.dll, and eventually it ends up marking the stack as RWX. But when EMET checks the return address and it goes back, it will see that this is validated because there's a legitimate call instruction which is going on. Now the next is return into shellcode. Now let's say that call and return are not available. So what do? Now EMET checks the return address. It doesn't check whether the return address has executable permissions or writable or readable. It doesn't care. It just checks whether the return address is preceded by a call gadget or not. So what do? You follow the same logic, and you make sure that you populate one register with whatever value you want to do, and you jump into it and make sure the return address is pointing to the shellcode. But now when EMET checks the shellcode, basically that area you can craft. So what do? You go a little back from the shellcode and you put a little call gadget over there because it's completely controllable by you. Even though it never got executed, it will still validate the logic and it will fail. The next one is SymExec flow. So SymExec flow is a little bit, it's like a call precedence check, but in a little hyperventilated form. So what it does is basically, instead of checking whether the return address, as in the return address is preceded by a call gadget or not, it will simulate the next 15 instructions, which is by default, and you can set up that any way you want. It will check whether the next 15 instructions are going into a return or not, and if they are going into a return instruction, they will check what particular return address is being given for that, and it will validate that return address for the caller check. So it's a little complicated, but I think we can get through it. So for that, we have a double call gadget or nearly 20 returns, very calculated returns, which can completely evade everything. So you can find this gadget called ESI, EBP, ESP, and EBX in the most popular DLL, that is MS-HTML. And what you do is, because there will be no return, so what do? You populate the first two non-volatile registers, one with the API you want to call, with the parameters, and the second one with the shellcode address you want to call, and you make sure you put the stack in such a way that this thing works out. So when EMET validates the call ESI, it checks, okay, fine, the return address is at call EBP. If you go back, it's call ESI, so it's validated ESI contains the proper address, so it works out. Then it goes forward into EBP, wherever it's being pointed, which should be the shellcode, and it will follow the next 15 or maybe, I don't know, depending on whatever the user configuration set up. It will check the 15 instructions, and it will check whether there's a return or not. But in a shellcode, I think you can safely put a knob sled before that, and that will work out, and the whole check will fail. The next is 20 return instructions. Now, finding a double call is very hard. It's not that easy. So the next approach, actually, we have seen this in the wild being used by, I think, Operation Clandestine Wolf itself. Yeah, I think so. So what they were doing was they would put up the virtual protect address inside a register, call it normally, and then make sure that the call that they do is done properly, as in this case it was called EX and return. And what they will do is, when you have to supply the return address after the API address in which you return into through the ROB gadgets, you put the return address as the return that is after call EX. And you make sure that you call the same thing like 15 to 20 times after that. So what eventually happens is, when virtual protect gets called, the return address is pointing to the return in call EX, return. So if you go back, you will see a call every time EMET tries to validate the logic. And by the time you hit 20 instructions, I think the buffer will expire. So at that time, this thing works out very nicely. So the next is EAF. So EAF is basically export address table filtering. What it does is, it will put up a hardware breakpoint on a very specific set of addresses, and it will check whether the address is being violated for read access, and it will check whether that thing is coming from a loaded module or not. So let's say that it has put the breakpoint on kernel base, kernel 32 and NDDLL's export address table, and the moment that access violation hits, because the shellcode has to grab the addresses from the export address of any loaded DLL, once they do that, the exception hits, and the context structure points to EIP, which should be the instruction pointer. That obviously will, in most cases, it will always belong to a region which is not the part of any loaded module. And EMET does the checking using PEB, so that is how it validates. And this usually filters out most of the Metasploit shellcodes, unless you have tampered with the shellcode generation mechanism. So for this, we have two evasions. One would be modifying the PEB. So what do? Basically, you can violate as much as you want, but we can play around the detection logic that EMET creates. So what we do is, we use the PEB to find out the first loaded module. That should be the executable section. And let's say the executable module is Internet Explorer's own PE image. Now you try to find that, and you start reading the first 1000 bytes. That should be the first page. And you take the current instruction pointer, you go back 1000 bytes and you start writing the same thing again. After that, you go and alter the PEB to make sure that the original image base address is not pointing to where it was supposed to be, and it's now pointing to your shellcode minus 1000. So when EMET tries to get the violation address and it sees whether this thing belongs to any PE loaded module or not, the PE check will work out. Why? Because we've simply copied the main executable's image before the shellcode. And the PEB check will also figure out, because it's essentially a part of loaded module, because EMET doesn't cache or kind of maintain any internal PEB list. It relies on the original list. So the next one is using import address table instead of export address table. Now, EMET has only access to 4 debug registers through which it applies the breakpoint. So it can put export address filtering on maybe 4 DLLs, but at the end of the day, if you're using the import address table of another DLL, which is kind of pointing to kernel 32 or let's say kernel base or even NTDLL, you can figure out some API addresses which can be useful later on, and the EAF check will not trigger. So this we have seen in the while attackers using MSVCRT and user32's import address table, and they kind of grab the address of get procedural address inside kernel 32, and from that they grab the address of whatever they want and then they call it. Because the EAF logic doesn't apply for inline hooking, it has to apply only on the hardware breakpoint. You can call whatever API you want after you have shellcode execution, and EMET will be completely evaded because of that. All right, so the next is targeted evasion. Now let's see that, let's say that individually reversing each and every protection, trying to figure out bypasses it's a little tidy. It's too hard of a task to achieve in a very less time. So rather than that, and if you think about any attacker who doesn't have much resources, who can understand this kind of stuff, they can simply look for EMET and figure out a way to evade that. Now the problem with this approach is it's very product specific. If EMET is not there, it will not work, and the failure chances are high. So it's similar to the disabled version, in which you find an offset and you terminate it and you put 0 over there. Because even in that case, if EMET doesn't exist, that offset doesn't exist, and the application will crash. So, and the advantages are it's very easy to deploy, it's very easy to find, to be honest, and it's basically a hook evasion using return-oriented programming. So, go forward. So, assumptions are obviously that we have all the DEP evasion APIs, like protect virtual memory, virtual protect EX, and etc. Or we can do cross-process tampering using write process memory, or we can do a one-shot DLL load from load library. So as long as we can call one single API, we can put in every effort that we want. Obviously, we can call multiple APIs, but it's good to make sure that the chain is as minimalistic as possible. So so basically the approach is you find the API address, and there will be a detoed hook over there, and you can check whether the function prologue is reachable from the detoed hook. And if there is a way to calculate the exact address to where you have to jump instead of to where you don't have to jump, we can jump to the saved prologue and we can completely evade all the hooks, and it will return back again. So I think Abdulellah mentioned something like this before for load library. Now, if you look at the same thing in virtual protect, what happens is basically this is the address for the API, and this is the D word for the offset. If you add to this address, you will reach this address. That's how a relative jump works. Now, through ROP gadgets, we can obviously dereference a pointer, we can add, we can subtract. That is, it's very common. So what we do is we take this address, we add 1 and we take this address, we add both to the API, and then we add 26 to this. So essentially we reach this area, and this thing works on quite a bit of EMET's versions. And what happens is you have an API address which you can call. It has a complete original prologue which was overwritten by EMET, and it also contains a jump which will go back and then complete the whole simulation of the API. So basically, this is an example of the chain required. The gadgets are not very difficult to find. It's just add and increase and move, and I guess that's it. So after that, what happens is we can do virtual protect without ever hitting EMET's hook, and we can get over it. After that, for the EAF check, again, we can do that. Obviously, with shellcode, that would be much easier compared to return-oriented programming. And if the possible chance of failure is it's very vital. Maybe somebody can use a little bit of conditional return-oriented programming to make sure that even though this fails, the application should not crash and it should exploit normally. So the application of evasion research. Now the problem with exploit detection products are that most of them have shared protections. Now if one product has to offer something, the next product also has to offer that, and it has to add something more additive to make sure that this thing sells. And sometimes there are few extra on each of them, sometimes they're even less than the other one if you compare multiple products. And some are modded over each other. Like with the example of collar check, the people who have taken the code from RobGuard again, they have only taken the check which basically validates whether the return address is preceded by a proper call or not. But nobody had the code other than obviously Microsoft to check whether the return address, the call gadget that was preceded by the return address is actually pointing to the hooked API. That would have been a little difficult. And because of this, if you evade one product, if the protection is not a very specific offset or a gadget view, it affects others. And because of that, if there is a design flaw, I mean, it works on all of them. And the main highlights of all the exploit detection products right now are return address validation. Basically, you hook an API and you check whether the return address is proper or not. You can put up some heuristics on that, which are a little more common. Just the loaded modules check is the most common. And you can do the exception validation, as in you can put up page guard, or you can put up page no access somewhere, or you can even put a hardware breakpoint. Again, that's limited a little bit. And you can then validate the exception for read-write access to make sure that this thing is proper or not. Other than that, the best one is attack surface reduction. You just simply block out something so that there is no bypass, there is no evasion, there is no way to go around the block. So the evasions are not very common in the wild, but the attackers are catching up. Obviously, Angler is gone now, but it's still the last we saw. It was evading EMET. It had a code inbuilt inside its framework, which was making sure that it was not checking whether EMET exists or not, because previously what used to happen was it will check if EMET exists and it will simply terminate. But now it doesn't check that, it just goes away straight away. And we have also seen 2015 2545 CVE evading EMET completely because of different mechanisms.
Yeah. Thank you.
Yeah, sure. Thank you.
Yeah. So we will talk now about the new technique to disable EMET using EMET. So we found there is a portion of code at this offset of EMET DLL that does unload EMET protections and remove them completely out of the memory. So this portion of code, instead of jumping directly to this offset, we can reach out this code from the DLL main when the right parameters get passed to the DLL main. The reason that we would like to use the DLL mains rather than jumping directly to the offset is that we could have this attack works against several versions of EMET instead of only one version at this offset, because from version to version this offset is going to be changed. So for just a refreshment about on the DLL main prototype. So the first parameter takes the base address of the DLL, which is the EMET DLL. The second and third parameter should be 0. The second parameter for DLL process detach. So this gives this gives the DLL process detach signal to the DLL main for the DLL to be unloaded. Also, the reserved, which is the third parameter, should be 0 or null. To get the base address of EMET DLL, we have used the get module handle API, which is unhooked by EMET because it's not being considered as a critical API. So this is an important portion of unloading code in EMET. We can see that it zero out some of the variable because after EMET gets unloaded out of the memory, these values are not going to be needed because this values has been unloaded. And there is a call on the left side to a function which does the actual batch, the hot batching in the memory. So it will remove out the installed hooks within these hooked APIs or detoured APIs. There are several data structures have been used within this unloading code. Actually, there are 3 of them. We will discuss 2 here. So EMET used this representation to represent the detoured APIs, the Windows detoured APIs, as a linked list of data structures. So this unloading hook, unloading code will loop through these data structure, linked list. For the detoured API data structure, there is a variable to show if it's active or not. Then there is a pointer to the second data structure, which gives more details about this detoured API. And there is the third pointer, which is just take you to the next node in this linked list. So in the second data structure, where there are more details about this detoured API, we can see there is a pointer to the detoured Windows API, and there is the detouring function, and there is the original prologue for this API before it gets detoured. Within the patch functions, which does the actual unhooking and removing out the installed hooks or detours, it walks through a linked list of hook config data structure. And here we describe this data structure. So there is a pointer to the next hook and the next pointer to the next node in this linked list, and there is a status is active. If it's active, then it's 1. If not, it's 0. And there is a pointer to the effective function. So after the unloading code runs, it will change this pointer. So instead of pointing to the detouring function, it will point to the non-detoured original API, because the installed hook has been removed. The detouring function or EMET protection function is not being used anymore. Then there is the detoured Windows API address, and here a pointer to it. And there is the EMET detouring function, which is a pointer to the EMET protection, basically. And I have colored this in blue, actually, because this one is being used in here. So actually, the unloading code has a call to memcopy, which will copy this, which will take this, that what I have colored in here as blue. It will use this as a pointer to retrieve the size and the detoured Windows API prologue. So it uses, so it's basically a pointer to a code, but it's being used to also to retrieve a size of the prologue and the prologue to be copied to the original to copy the original prologue to the detoured API. So before calling the patch function, we can see the load library. There is a jump at the top, so there is an installed detour in there. After this, after we return from patch functions and it's done looping through all the installed detours, we can see that the original prologue of the load library has been restored. To disable the AEF protection, which uses the debugging registers, EMET continues with the unloading code. So it will at this offset of EMET DLL, EMET uses zero out the context structure we have discussed earlier, and then use the memset to zero out that. And then EMET calls the anti-set context thread to set that zero out context to the current thread, and to make it effective and disable the AEF protection. So we have, for the exploit implementation, we have took an old exploit for Firefox, and we installed EMET 5.2.0.1, and we have added our rob gadgets on the top of that exploit. So basically, we wasn't trying to jump directly to the offset as we have discussed earlier. We was trying to locate the DLL main then we are trying to send the right parameters to get to the unload code. So basically, there are some considerations here we have considered during building our rope gadgets. So we know that we could retrieve the emit base address with using git module handle. Then we know that the MZ signature or this header, it's located on the base address, and from there we can, with a certain offset, we can locate the PE header or signature. All of this just to get the offset for the address of entry point at certain address gets added to the PE header, and then we just call the DLL main, which is the base address basically added to the address of the entry point, the offset we have found in the PE header. And then we call it with the right parameters. And this will result in calling the unloading code. This is the actual rope gadgets we used, which have been described in the previous slides, so no need to go through them entirely. So the advantages that this technique gives is that it's easy. You can see that it's straightforward rope gadgets, and it's reliable. Nothing can be more reliable than having EMET unloading, disabling itself. And it write once and exploit everywhere. So it works for EMET, different versions of EMET actually, because we are utilizing the DLL main instead of just jumping to a certain offset. And it also, there is no special treatment for the EAF protections and the EAF plus, because EMET will continue with the unloading code and will disable them off. One question that I have came across over the internet on Reddit. So this guy was asking how Microsoft fixed this issue, because rather than the DLL main, it's essential, and the DLL process detach signal is also essential to EMET. So how did they fix it? So I have digged a bit to see how they fix it. So additional checks have been added to the DLL main. So it's no longer that just providing these parameters to the DLL main will take you to the unloading process, to the unloading function. Sorry. Also, I have found that unloading code is still there at a different offset of EMET DLL. The detoured API structure and the hook config structure that we discussed still exist, but they are ineffective because of the fix. So the actual fix was to pivoting this pointer, which was being used in the previous version of EMET, to retrieve the address and the size of the original prologue. So right now it points to the hook address and the size of that hook. So even if one could succeed calling this mem copy and defeats all of the additional checks, it would result in rewriting this hook rather than just removing it. And this is how they fix it.
Yeah. All right. So, I mean, just like you saw, there's a big design flaw in EMET's DLL, and it not only applies to EMET, but it will go anywhere, because a DLL has to have unloading code. So this brings us to the next point, that is the importance of custom exploit prevention techniques. Now, you saw the previous slides. What happens is you roll out a product, or you roll out a tool or anything, and you challenge the attackers, and eventually they will strike back, even though it takes time. The problem is security through obscurity is not. It's a failed model, all right, but it gives you more time. It gives you more time to implement more protections. It gives you more time to, for the bad guys to even understand what's wrong. And suddenly one day their exploit is working, and suddenly the next day their hit rate is, let's say, 2-3% less. Why? Because of some detection product that is coming and blocking up. So it's always more advantageous to have multiple protections, and it's even better to have a custom one, because eventually you'll realize that if you use something which is public, everybody has access to that, everybody has a code for that, and reverse engineering simple tricks and all the protections and trying to find out bypasses, it's a little difficult, but it's still true. And other than that, evading very simple hooks and like leaving out the exception handlers or using something else, because ultimately the detection technology over here revolves around that. And if we don't do that, essentially it gives us we are kind of on a back foot for that. Not only does it gives us more advantage, but it's more effective telemetry. You have 3 products, and we had the sample in FireEye for Angler exploit for CV 2015-2545. Yeah, all of those evaded EMET, but some other detection product eventually caught it, and that is how we found it, because there is no other way you can find out how it works. Because if one is failing and the other is catching, it's a good thing. So I think that's it. So we have the acknowledgements. Thanks to our colleagues who helped us in figuring out this stuff. And you have the demo, right?
Yeah.
All right, go ahead. So Abdulellah will show you the demo on the event stuff.
So we have this exploit. We will see how EMET will respond to this exploit. We see that EMET detected the stack pivoting in this exploit. So this is the other exploit, which has our rope gadget, and our rope gadget just called the DLL main with this parameter. Let's walk through this in action in the debugger. So this is the beginning of the unloading code, starting with removing the hooks. So we could see that the EAX is pointing to the detoured API config, which gives more details about the installed hooks. About the detoured APIs. We can see that the set context thread is being unloaded. We can see the jump. This is the installed detour. If you follow this, it will lead us to the detour, to the EMET detouring function. So, and we see that it zero out this value because it's not going to be needed anymore. This is the EMET detouring function. So this is the call. We have jumped over all the installed detours. We will go to the batch function to see how the patching to patch out the installed detours. Yeah. So now the ASI points to the installed hooks. This is the mem copy we talked about. We are seeing the first API being patching by using the mem copy. We can see the source which being patched with. So we are seeing this is the installed detour. It's being detoured right now, and the mem copy which will be executed right now. We'll see how it will affect this API. We can see that this is the original prologue gets copied onto the top of this API. So it has been unhooked then it works through all the other installed hooks the same way, this time with continue API. So we will skip this. Right now it's trying to disable the AEF protection. We can see it's memset, this structure, the context structure. Zero out everything, and then calls indirect call to set context thread with this context, and you can see the if E at the end. This is the current thread. These are the parameters to set context thread, which will disable the EAF protection. You can see this is the context structure, has been zero out. Let's check load library, for example. You can see it has been just git patched. No protection for Amit in here. Now we would run that to see how it works. We can see the calc pops up and it's working. Yeah. Thank you.
Thank you.
Thank you.
Time up.
Thank you, guys. So I think we are ready for the questions.
If there is time.
Yeah.
All right.
Yeah.
You can go.
Excellent, thank you. And if anybody has any questions, we'll be down here, but we'll need to make room for the next speaker. So thank you.
Thank you. Thank you for attending. Thank you.